Great. All right, welcome. This is the week 6 webinar. So we're halfway through because it's a 12-week class. So when we're done with week 6, we'll be halfway through the course. And so thanks for coming. Let me tell you the plan today. I will answer any questions as always if you have them, and that could be now or any time. I'll be watching the chat box to make that work. And feel free to type that in. And then after that, we're getting into confidence intervals. So basically, for the rest of this entire class, it's all about applications. So it's how to look at data and then decide what you can say about it. And what we're going to be looking at are confidence intervals this week, which is a very important topic. So we'll start out with confidence intervals for means. So we'll see what that means and what it's all about. We'll then look at confidence intervals for proportions. And then after that, we'll look at sample size for means. So how big a sample size do you need in order to have a pretty good data set that will be what you want? And then same thing with proportions. So that is the plan. Just a few notes. So the project one was submitted yesterday. I've started just the very beginning of grading it. I taught most of the day today, so Mondays are my busy days. And tomorrow I plan to do a whole lot more of grading, and I maybe finish. If not, it'll be definitely by Thursday, but probably by Wednesday, if not tomorrow. So that's my plan. And at this point, if you haven't finished, if you didn't submit it, you didn't submit it. So hopefully you submitted your project. So that is a requirement. And it's not like there's a surprise. I've been talking about this every week. And you'll see your grades and just note that the person who submitted, I put on lots of feedback throughout the paper that was submitted. And then it'll be your responsibility to share that feedback with your partners because that's kind of where it's only one person sees it, but then they can share it with other people. So that is, my request is please share it with the partners. I'll type that in my comments also for you to share it, and you'll see your grade. So I graded one of them actually, but there's a whole bunch more. And tomorrow I have not all day off, but I only have a few hours that I have to do other things. So I'll definitely have some time to work on the projects. And if more than one submitted it, which you only one was supposed to submit, then what I do is I grade the one first in alphabetical order, and the other person I say, hey, ask the other person to look at the comments, and everyone on the in the group gets the same grade. Just a note. So hopefully it went well because that was project one. There will be project two, but really next week is the time to talk about project two. But this is week 6. What's important about week 6? Hopefully you all know by now. What's that? That number is important. Yeah, it's an even number. So don't forget that there is an exam this week. And the way it'll work is it'll be on the chapter we're doing today. So we're doing the chapter on confidence intervals, and then it will also cover, in terms of the 50% of it will cover that and last week's stuff. And the last week's stuff was essential limit theorem. So it's chapter 7 and 8, basically. And then chapters 1 through 6 will be the other half. Okay, so that's important to note. And today I'll show you kind of the wording that you're going to need to have to, get full credit, to get good credit on the exam and also on discussion forums. So are there any questions? Are there any questions that you have about anything? And hopefully I'll see a screen, right? The Q&A and conference center for means, all that. Just want to double check that it's all visible. Do you see it? 1, 2, 3, 4, 5. Do you see all this? Good, good. Just want to make sure that it shows. Because I think there was an update to Zoom and it doesn't show me everything. So I have a question for you. I know it's a small group, but we'll do our best. At least it's not a group of one that you really can't do much with. And here's a question. I ask this pretty much every time, every year I've taught this class for decades, and I've watched changes. So the question I have for you, and you have to put in the chat box, is how old were you when you experienced your first passionate kiss? And by the way, if you don't want to tell everybody, at least make something up that's reasonable. Don't say you're 195 years old because that can't happen. And passionate kiss is not like your dad kissed you when you were one. That's not a passionate kiss. That's a family little kiss. And put in the chat box how old you were. Okay. And if you've never kissed anyone, then had a passionate kiss, maybe how old you are now. And let's see, I want everyone to do it because we have too small sample size for not everyone to do it. Okay. So what we have is 19, comma, 20, comma, 26. Okay. It's very small sample size, but hey, we'll do it. And as I mentioned, I have been asking this question for 30 years now, 31, I think. And I've seen a difference. I've seen a difference from then to now. Things have changed. Cultures change, and that's always interesting. So there's going to be a lot of things we want to look at is, okay, we have that. And what we can do is let's assume the population distribution of first passionate kiss age is normal. Why am I going to have to assume that the population is normal? Do you remember from last week? Any thoughts? Why do I have to make that assumption in order to do anything statistically interesting? Any thoughts? There's a good reason. We've talked about this already last week. Don't see y'all jumping in. Okay, so notice, yeah, we need to, well, we're assuming it's normal, but the reason is our sample size. Our sample size is 3, which is a really tiny sample size. How big a sample size do you need so that you don't have to make that assumption that the population distribution is normal? Do you remember? How big a sample size must you have? Yeah, greater than 30. So the smallest sample you could have would be 31. We're not even close. So we're going to assume the population distribution is normal. Sound good? We can take 19, 20, and 26. I can go to the calculator, and I'm going to go to the one variable stats calculator. And 19, comma, 20, comma, 26. And this is a sample, and it calculate. And what we get is we get a mean of 22.6. Okay, so that is our X bar. And again, that was 22.6. We get a sample standard deviation of 4.8083. And our sample size was 3, tiny. And our standard error, if you remember, we had a formula for that. So that formula, if you remember, was the square root, which I'm not seeing that square root. Let me see something. I think I have to undo and redo. So that formula now, there we go, was the square root and that was sigma over root n. Now we only have s, and we're going to live with that. It's not the best. So let's do it. And s was 4.8083 divided by the square, divided by, oh, sorry, it's not the square root of all that. It's one more time. It is 1 over, it is sigma, which we're going to call s, which is 4.8083 divided by the square root of 3. Okay, and that is basically, let's figure out 8083. So if I go to the calculator, and we take the square root of 0.8083. Let's see, 4.8083. Divided by the square root of 3. I get about 2.776. Any questions on that? Okay, so that was our first step. We now know we have a standard error. We have an X bar. We're pretty good. We did make one little issue, and that is I'm using the sample standard deviation instead of the population standard deviation to find the standard error. And I have to do that because we can't know the population standard deviation of, let's say, all college students' first age of, passionate kiss. Does that make sense? So we're making that as an assumption. So here's what we're going to do. We're going to realize we're making the assumption we have a normal distribution. And what I want to do is my best guess for the population mean is 22.6 years old. Is that clear? That's my best guess because that's all I've got. Okay, just have X bar, and that's just best guess. We don't know the population mean, but that's our best guess. Our standard error was about 2.776. So if I go to the left 2.776 and to the right 2.776, that will give us a confidence interval. Okay, except that will be the standard error, but I'm going to need to realize that what I want, that'll give me some kind of error, but what I want is a 95% confidence interval. Okay, so I want to say, well, how far left and right do I go so that 95% of the area is between those two numbers? Any questions on the idea of that? So that's what we're interested in. Okay. Now, I can't know for sure what that is. I can do some calculation, but let me show you an easier way. And I'm going to go back to the calculator menu. And I'm going to go to, any guess on what calculator number I want to do? We could do number 10, but what we got is data. We have 3 numbers, right? So I'm going to go number 11, confidence interval for a mean with data. And our data, do you remember, was 19, 20, and 26. And let's be 95% confident. So 95%, 0.95. And I hit calculate. And that's a much easier way to do it than to sit there and try and calculate it using the central limit theorem and all that stuff. I created a calculator that does this for us, does everything for us. Okay. And what it's going to give us is now the lower bound and the upper bound of that confidence interval. And the lower bound is about 12.26, and the upper bound is 31.07. 12.26. The upper bound was 31.07. Any questions on how I got those two numbers? Okay. Now, you probably really don't care to the, 2 digits. Maybe one is good enough. So that's 12.2 and 31.1. Notice it's very wide, by the way. And that's because we had a sample size of 3. And when you have a sample size of 3, it's awful. Okay, you should never do anything with a sample size of 3, but that's all we had to do. Any questions on that? Okay, so here we go. There's a big issue. And if you think what we did is use the central limit theorem, and then we use the normal distribution calculator, there's a problem. And the problem comes from the fact that we're using the sample standard deviation, and we don't know the population standard deviation. And it turns out that gives you additional error. And you don't get the normal distribution exactly. You get something that's not that far from it, but with a sample size of 3, actually, it's pretty far. Okay, but if you have a bigger sample size, it's not that far. So we're going to use a different distribution, which doesn't look that much different than normal distribution if you have a larger sample size. And that is called the student's t-distribution. So the person who came up with it, the person did a couple things. One is taught statistics and decided to name it after his students and called it the student's t-distribution. Okay. And the way he found out that this worked and realized that using the normal distribution didn't work, believe it or not, it had to do with beer. He was actually working for a beer company and he was doing statistics based on samples of beer and he realized it wasn't working. So in order to make it work, he came up with this student's t-distribution. The math is very intense. We're not going to do that. You just have to trust it. Sound good? Okay, so that, but it's important that we know that there's a different distribution. Okay, so student's t-distribution will be the distribution that's being used with the calculator that finds the confidence interval. All right, so now we have to interpret what this means. Okay, so we've kind of looked at this kind of as a curve, and we say that, hey, there's a 95% chance, but randomly selected, it'll be between those 2 points. That's kind of how this was calculated. Okay, and that's why we called it a 95% confidence interval. Can you choose a different percent besides 95%? What do you think? Do you think it would work if we wanted to say, hey, how about 90%? And if it was 90%, then it would be a narrow interval because then you're 90% of the graph. 90% is under the curve. And then you can go in a bit. Do you think you can use 90% instead of 95%? What do you think? Any thoughts? Yes, no? I don't see anyone jumping in. It's not a trick question. No idea. Okay. Turns out you can use whatever percent you want, but you have to understand what the pros and cons are. If you use a 90% confidence interval, then you're going to say, now the age of first kiss is like here, between here and here, I got a good precise estimate. But the problem is there'll be a 10% chance that you're wrong instead of a 5% chance you're wrong. Right? If you really don't want to be wrong, you could do a 99% confidence level. Okay, but that's going to make it really wide. So, yeah, you're going to be right almost certainly, but you're going to have such a wide confidence interval that it may be useless. Like if you could say 99.99% confident that the age of first kiss is somewhere between 0 years old and 200 years old. Well, of course, but who cares? We all know that anyway. Does that make sense? So it turns out that the standard, especially in social science, an age of first kiss is a social science thing, is 95%. Doesn't mean it has to be used, but that's the standard for social science. Okay. If there's a lot of damage done by being wrong, then you might want to choose a 99% instead. Okay. If there's if you want a really narrow interval and there's no damage done being wrong, you might want to go for the 90%. In our class, we're going to do 90%, 95, and 99. Those are the three choices. Because it's elementary stats, we can only do so much. All right, so now it's time to interpret this confidence interval. Okay, so I typed this out, but I didn't put it all in. So let's put it in. Okay, so what we can say is with 95% confidence, we can conclude that the population mean age of first kiss among 3 students. Okay. Oh, among all, so among all students is between, oh, I see. No, I know I had it. Community college students, California community college students is between 12.2 years old and 31.1 years old. Okay. I want to note something. I screamed and yelled, and you can highlight, I highlighted the word with and the word population. I'm going to remind you, if I do that, what do you know you have to do? If you don't put those words in, what's going to happen? So those 2 words, you have to start with the word with. So when you have to interpret the confidence interval, the first word must be with, and you must refer to the population. Is that clear? If you don't, I take off points. And AI won't always do it, by the way. So just a note, take notes. Okay. By the way, this confidence interval is not that useful because 12.2 years and 31.1 years, that's a huge span. So we haven't really learned anything. And really the reason that we haven't learned much of anything is that there are only 3 students. Okay. If we had a sample size of 40, you'd have a much narrower confidence interval because of this over root n. Sigma sub x bar is sigma over root n. So if n is much larger, then you'll have a more narrow or more precise confidence interval. Any questions on that? Okay. I do want to let you know if I say interpret the confidence interval, then it's this wording. On the other hand, sometimes you want to say, well, let's interpret the confidence level. Okay, so what does it mean to be 95% confident? Which is different than asking for interpreting the interval. So here's how it works. If many samples of sample size, in our case 3, are taken, then each one will result in a different confidence interval. So if we did this for a living and we asked another 3 people, we're going to get a different confidence interval. We asked another group of 3, you'll get a different one. You could do this, many, many years, and you could say, well, what percent of your confidence intervals will contain the true population mean age of first kiss, of the age of first kiss? 95% of these confidence intervals will contain the true population mean age of first kiss. The other 5% will not contain the population mean age of first kiss. So it's kind of like, imagine, you run a newspaper company, news company, and if you're 95% confident, that means that 95% of the time, what you publish is going to be correct. And 5% of the time, you're going to publish something that's not right. Okay? And one of the things you always have to decide is that good enough? Okay? If you need to be 100%, it'll never happen because you can't get, for example, a survey of every California community college student. It's not possible. There's millions of them. Does that make sense? So you have to take a sample. You cannot get the whole population. Any questions at all on this idea? Okay, so this is a big deal because when you take a sample, you want to say, what is my estimate and how far am I off by? Okay, so what's the low and what's the high that you think it probably is? Because the sample mean is not going to be exactly the same as the population mean. But you really want to say, well, how far off do I think I might be? And I'm going to be 95% confident that it's within these numbers. Any questions on this idea? Any questions? All right. Just a note, here's a template for the interpreting the confidence interval with whatever percent confidence. It might be 95%, it could be 90, it could be 99%. It can be concluded the population mean, whatever you're talking about, in our case, it's age of first kiss, is between the low and the high. Okay, any questions on the template? Any questions on that? Okay. By the way, do you think the population mean age of first kiss has changed in the last, since I was a kid, for example? So in the last, 45 or so years. So, by the way, my first kiss, I was 13 years old. Was I old or was I young? Any thoughts? Look how old you were. I was 13 years old when I had my first passionate kiss. So was I old or young? You can type it in. Any thoughts? Okay. And I'll let you know I have been doing these confidence intervals for a long time. Any thoughts? And I've also researched it, not just from my data, but for big data. Okay. Right. You may think I was young, but everyone laughed at me. They thought I was like just some nerd because I hadn't had a kiss yet when I was, just turned 13. I was like 13 years old in a month or so, or something like that. Uh, so I was actually really old for my generation. Things have changed. And we know that because they've been doing these statistics for many, many, many years. And I look at it every year. And the age at which people start having first passionate kiss, having sex, having children has really changed in the last, 45 years or so. Okay. And to me, I think it's really cool to look at the statistics. And if they don't do statistics, if they don't collect data, you wouldn't know. That's something you have to do by surveying. So confidence interval is the best we can do. If you have a large enough sample size, then you get a nice narrow confidence interval where this one was awful. 12 years to 31 years is way too wide. Any questions on this? Okay, just note the template for interpreting the confidence level is similar to what we did for interpreting the confidence level for age's first kiss. If many samples of whatever your sample size was are taken, then each would produce its own confidence interval. Okay. And if you have a 95% confidence level, then 95% of these intervals, if it was 90%, be 90% of these confidence intervals will contain the true population mean of whatever you're talking about. In this case, it's age of first kiss. And 5% in our case, because that's 100% minus 95%. 5% won't contain the true population mean. Okay. And as I mentioned earlier, you still have to have a sample size over 30 if you don't know that the population distribution is normal, and you almost never do. Any questions on that? Any questions? Okay, so now let's do another example that's going to be a different type. And what percent of all adult Americans volunteered their time in the last year? They've all even put in the last year. Okay. And this is one that I found online. I went to Gallup, and this is what they said. They did a survey. They asked 1,016 adult Americans, "Hey, did you volunteer your time in the last year?" Any questions on that? And what they got was that the p hat, which is the sample proportion out of the 1,016 adult Americans, was 0.63, 63%. Okay. And by the way, I have volunteered my time in the last year. Okay. I'm not sure if all of you have also, but definitely have a lot of people who have. Okay. By the way, the number of yes answers, if we take 1,016 and multiply by 0.63, I got 640. Okay, now we're talking proportions. So from the central limit theorem, we need that to be bigger than 5. And it certainly is. Okay, we also need, so we also need NQ. That would be the number of people who said no. And that was 376 answered no. So if you take 1,016 and multiply by 1 minus 0.63, you get 376. And that certainly is also greater than 5. Any questions on that? So it is important to always check that NP and NQ are greater than 5 when we have proportions. And you can say it's proportions because the survey question is, let me ask you, put in the chat box, in the last year, have you volunteered your time? Put your answer. Have you volunteered your time in the last year? Have you? Okay. So not how much time have you volunteered? It's have you volunteered your time? Does that make sense? Yeah. So the answers that you gave are either yes or no. So when you have a yes/no question, we're talking proportions, we're not talking means. So this is not about being over 30. This is about being NP and NQ being over 5. So common mistake people make. Always, always think about what is the survey question? And if the answer would be a number, then you can do means. If the answer is going to be a yes or a no type thing, it'll be proportions. Any questions on that? Okay, so now we want to say, can we find how about 95% confidence interval for this? So let's go to our calculator. Can we use this calculator? What do you think? Can we use it? Put in the chat box, yes or no? Can we use the calculator? This one? Should be quick. Yeah, the answer is definitely no, because this is when you have quantitative data. We don't. We have a bunch of yeses and nos. Do you see that? So we're going to go back to the calculator menu. And let's see if you can tell me what calculator to use. What number? Yeah, number 13, because confidence interval for a proportion, because it's a yes-no survey question. And what it asks you for is n. That was the sample size. That was 1,016. Then it asked for x, which are the number of yes answers. That was 640. Okay. And by the way, if you take the percent, multiply by 1,016. That's how I got the 640. And you always have to round to the nearest whole number because you can't have a fractional number of yes answers. Can't have a third of a person say yes. So it's 640. We'll do 95% for the confidence level and hit calculate. Any questions on this? Okay, and this gives you the picture. Okay, under it, you think it was the normal distribution, but it's actually the t-distribution, but it's not that different. No, I'm sorry. This is a normal distribution because it's a yes/no question. Sorry about that. And good enough close approximation. Our lower bound is about 0.60, and our upper bound is about 0.66. Okay. Any questions on using the calculator? Okay, so here's the confidence interval. And if you round it, you get 0.66 and 0.60. And it turns out this is an important word. It's called the margin of error. The margin of error is the distance from the center, which is about 0.63, to the edge. And it's symmetric, so either left or right, it doesn't matter. And that distance is the margin of error. So notice 0.63 to 0.66 is 0.03. And similarly, 0.60 to 0.63 is 0.03. So the margin of error, you can also take 0.66 plus 0.60 and divide by 2. And you get 0.03. That's called the margin of error. And what you'd like is a margin of error to be small. You don't want a big error. You don't want a wide confidence interval. You want a small one. So the only way to get a smaller confidence interval, a narrower confidence interval, is a larger sample size. You could go to a lower confidence level, and that will work also, but then you have a higher chance of being wrong. Okay? But if you have a sample size bigger, then the good thing about that is that you can stay with 95% and get a smaller margin of error. The bad thing about that is it's a lot of work to ask another, 1,000 people or a couple thousand people. It takes a huge amount of work. Any questions on these ideas? Okay, so now we can interpret it. So we can say with 95% confidence, we can conclude that the population proportion of all adult Americans who volunteered their time in the past year is between 0.6 and 0.66. Okay, notice, by the way, the word with and the word population, and also the word proportion. Okay, you talk about a proportion if it was a yes/no question. You talk about a mean if it was a quantitative question. And don't mix those up. You'll lose points if you mix those up, and a lot of people mix them up. Okay, keep in mind whether you have a proportion or a mean. So don't just copy and paste this for every answer. Make sure you understand it. Okay. The other way of saying it, which is pretty similar, is with 95% confidence, between 60% and 66% of all adult Americans volunteered their time in the past year. It means the same thing. Some people like this better because it's easier to understand. But again, just like I said, you had to have the word population before. Now you have to have the word all. So you're still referring to the population and not the sample. If you refer to the sample, it's wrong. Any questions at all about the confidence interval? Okay. We could also interpret the confidence level, very similar to the last example. If many groups of 1,016 adult Americans are surveyed, then each group will result in its own confidence interval. 95% of these confidence interval will contain the true population proportion of all adult Americans who volunteered their time in the past year. And 5% of the confidence intervals will not contain the true population proportion of all adult Americans who volunteered their time in the past year. So in the way, 95% of the time you're going to be right that the population, the proportion really is in there, but 5% of the time you're going to say it's in there, you're 95% certain, and then it turns out it's outside, either left or right. Any questions on this idea? I do want to give you a heads up. There's a lot of writing. Be ready. Okay, you don't just say it with 2 or 3 words. There's no short answer. You have to do a lot of writing, especially for interpreting the confidence level. Any questions on this idea? Okay, it's used a lot. It really is a lot. Okay, you'll also hear sometimes people will say that, hey, they got a sample proportion of 63%, and the margin of error was plus or minus 3%. So you'll see that also when you read publications and news and all that kind of stuff. Okay, so hopefully this is making sense. And you may or may not have heard confidence intervals talked about before, but when you look at published articles, so real stuff, not just kind of silly news, this confidence intervals and the margin of error is used all the time. It's very important. All right, I got a secret word for you now. Secret word is many. Okay, secret word is many because when you're interpreting the confidence interval, confidence level, you're saying if you did this many times, okay, if you surveyed 1,016 people many, many times, then 95% of them, of the confidence intervals you're going to get, will contain the true population proportion. So that's why many. So that's the secret word. Don't forget to write it down so you don't forget it. Now we're going to do more stuff. Let's do sample size for the mean. Okay. So sample size for the mean. And by the way, we probably will finish a little early today, which is always good, but you never know. So the central limit theorem, if you remember, had sigma sub x bar as sigma over root n. Is that clear? So the error is going to be the z-score times sigma sub x bar, which is z times sigma over root n. So then what we can do is we can multiply by root n, divide by e, and take a square of both sides. A little bit of algebra. And you get n is equal to z sigma over e squared. Okay, and that is going to be the sample size you need in order to have the margin of error that you want with the confidence level that you want, and z will be the z corresponding to that percent, times the standard deviation. and then squared. Any questions on that? Any questions? Okay. All right. So, oops. All right. Let's suppose we had, if you look at our original confidence interval that we had a confidence interval between 12.2 and 31.1. Okay. That that is way too wide. Okay. That doesn't give us much information at all. Do you agree? Oh, what see, what's the difference between root square n and another n? Um, Let me go down to that. So I'm not sure what you mean by root square n and another n. This is the square root of the sample size. That's all that is in the formula. And this is the n when you did algebra. I solved. Do you see? So n is the sample size needed. So it's not different things. It's the same n. Do you see that? The square root of n and n are different because if you take the square root of a number, you get a different number, right? Square root of 100 is 10. Do you see? Does that make sense? Yeah, so that's just in the formula. Okay. So again, if you look at our original, our confidence interval was way wide, 12.2 to 31.1, way wide. And the reason why it was way too wide to have any good information was our sample size was just too small. Does that make sense? So a question would be, let's suppose you didn't want this margin of error. This margin of error is gigantic, right? This margin of error is, it's like almost 10 years, 9.5 years old. So let's suppose you wanted a only 5-year old margin of error. Okay. And by the way, our standard deviation was 4.8083. So if we wanted the margin of error to be no more, and by the way, um, in our case, our standard deviation was 4.8083. If you wanted the margin of error to be no more than 0.5 years old, so a half a year old, okay? So you want the margin of error to be just 6 months old instead of like so old that we had so many years. How large a sample size would you need? Okay, now we could plug it into this formula. Now it turns out there's an easier way. Any guess? Yeah, yeah. So what we can do, not this one. I go back to the calculator menu. And what calculator should we use? What calculator number? Yeah, 12. This is about a mean, right? We're talking about the average age of first kiss. The mean age is quantitative data, and I want a sample size. It says, what is sigma? Sigma was 4.8083. We want a margin of error to be 0.5. We still want a 95% confidence interval, right? Okay. So 95%, and I calculate n, and it gives me 356. Okay, you do need to use this calculator. If you start doing other things, you're going to round off wrong, and all kinds of things are going to go wrong. So you do want to use this calculator. I will take off points if you don't. Okay, if you use AI, it won't. So you do have to use this calculator. That's required. Don't use AI. Got it? Okay. So we would have to survey 356 California community college students. Okay. It's a lot of work. It's a whole lot more than surveying just three. But if you do survey 356, you'll get nice data. You'll have a margin of error of less than at most a half a year old. Okay. So then you'll know, for example, hey, the average age of first kiss is between 21.2 and 22.2, something like that. Then you'd have a margin of error of a half year. And then you really have a good idea. Is that clear? Any questions on how I did this? Just notice if instead we wanted a 90% confidence interval, 0.9, notice we'd have to survey not as many people. So if you're okay with having a bigger probability of being wrong, you don't have to have the biggest sample size. If you wanted a 99%, then you have to survey 614. It's really big. Do you see how that works? So I tried to make the calculator easy, but you do have to plug in the numbers. All right, so here's another one. Let's suppose you wanted to find a 90% confidence interval for the population mean hourly wages of nurses in California. Let's suppose, based on a preliminary study, the standard deviation is assumed to be $25 an hour. Okay, by the way, standard deviation does not mean nurses only make $25 an hour. It means that they vary by pretty much money. Some make more money, some make less money per hour. Does that make sense? If you want the margin of error to be no more than $2, how many nurses must you survey? So we just go to the same calculator. We want the standard deviation to be, the standard deviation is $25. Okay. And you usually do a preliminary study. So basically you ask a smaller sample, one that you can handle, and then you say, yeah, that's our best guess. The margin of error, we want to be no more than $2. Because $2 an hour isn't that big a deal when you're looking at nurses' salaries. And we wanted a 90% confidence interval. And it calculated. So we'd have to survey 423 nurses. Any questions on this? Okay. So just a note, and this is important, you could do the same idea for the population proportion. And you can come up with the sample size you need for a confidence interval for a population proportion. This is very important because if you're going to be, doing a study that's real, you want to say, well, how small a margin of error do I want? What confidence interval do I want? And then you're going to find the sample size needed so you know how many people you need to survey. If you survey too many, what's the problem? What's the issue if you survey too many people? Any thoughts? Yeah, it's too much work and it costs too much and maybe it takes too long. By the time you're done, maybe no one's interested anymore. So it's a big waste of time and money to survey too many people. If you don't survey enough people, what's the problem? That has a different issue, very different issue. Sure, this could be cheaper. But what's the big issue? If you don't survey enough people? Any thoughts? Okay, let's see how jumping in. You cannot represent the population. Let me put it in what we've been doing though. You're going to have too big a margin of error, and you're going to end up having meaningless data, like knowing between age of first kiss is somewhere between 12 years old and 31 years old. That doesn't tell anyone anything. Do you agree? So you end up with nothing very useful. Okay. So it's really important to do this research before you collect your survey, conduct your survey. So let's do an example. So suppose you want to find a 99% confidence interval for the population proportion of cars in the United States that are electric vehicles. If you want the margin of error to be no more than 3%, how many cars must you look at? Okay, so we can't use this calculator because that's for a mean. So I can go back to the calculator menu. And which calculator do I use? What number? Yeah, it's 14. It's 14 because we want a sample size and we have a yes/no survey question. Okay, so now we have to say, do we have any idea what P is? And so far, for part A, we don't know. We don't have any information about that. Okay, we want a margin of error of no more than 3%. So we don't have an estimate for P. Margin of error of no more than 3%. Don't forget that has to be turned into decimals. 0.03. Confidence level of 99%, so 0.99. Any questions on that? And I calculate end. And I get 1,844. Okay, which is a lot of work. And we saw that in some of the examples that we have, and something I mentioned, you typically need more than 1,000. Typically need more than 1,000 to have a reliable confidence interval, a good sample when you have a yes/no survey question. That, by the way, just to let you know, will be one of the reasons why you're not going to be doing a yes/no survey question for your project 2, because it's too much work because you'd need more than 1,000 people to ask or 1,000 data points. And I don't want to do that to you. So that's just a note that you do need to put a lot of effort into it. Any questions on finding that sample size? Okay, if you look at last year's data, 8% of all cars were electric vehicles. How many cars would you need to look at for a 99% confidence interval? What's different? What's changed? Why is this different in terms of the calculator? Yeah, now we have an estimate for P. So I can click have an estimate for P. Now it asks for that estimate. And that estimate was 8% or 0.08. And I'm going to hit calculate N, and instead of 1,844, I only have to survey 543. So notice that made a big difference. If you have an estimate for P, and especially if that estimate is much smaller than 50% or much larger than 50%, then you're not going to have to do as big a sample size. Okay, I'm not going to spend that much time with the math, but you can trust me. Or you can do the math yourself and you'll find out that it matters. If you're real close to 0.5, it won't make any difference at all. If you're exactly 0.5, it makes no difference. So had your estimate been 0.5, you get the same number, 1844. It turns out having the estimate of 0.5 doesn't help at all. But 0.03 makes a huge difference. And 0.08 makes a big difference, but not quite as big a difference. Do you see? Any questions on this? Any questions? Okay. Maybe I'll ask one more question because this is helpful. Let's suppose, let's suppose we did a study. We'll even look at our study. And that was this one. And we had our margin of error was really wide. Let's suppose that you wanted to cut the margin of error in half. How big a sample size would you need? And the idea is that now we're not going to use the regular calculator because we can just do it. Any ideas? If you wanted to cut the margin of error in half, instead of a sample size of 3, because that's what we had, what sample size would we now need? Any thoughts? Okay, so let me show you the key. The margin of error is proportional to the standard error, which is sigma over root n. Okay, changing the sample size. Well, if we say doubled it, the problem is we're going to cut it by 1 over root 2 as a factor. If we want to cut it in half, we'd want 1 over 2. So we want n to be 4 because the square root of 4 is 2. So if you wanted to cut your sample size by a factor of 2, then we would need 4 times the people. We'd need a sample size of 12 because 4 times 3 is 12. Any questions on that simple math? Okay, if we wanted to cut it by a factor of 10, then we'd have to say 10 squared. And that's 100. So you'd need 100 times more. You'd need to survey 300 people if you wanted to cut it by a factor of 10. Any questions on that idea? Hopefully I didn't lose you. Okay. So as I mentioned, we can cut it a little shorter than usual because this isn't too bad, but I'm always happy to answer questions. I think I'm going to stop the recording now.